Welcome to Obhi's Math e-Pathshala. Today's topic is normal subgroups. Let's start the session.
So today we shall explore some important facts on normal subgroups of a group, and we will see that these normal subgroups will play uh, an important role in the theory of groups. So first of all, it will give you some indications to construct new groups out of the old ones, and out of these new groups you can find out more uh, important types of groups in the uh, study of our group theory. Okay. Okay. And specifically speaking, if you want to study normal subgroups, you will see that it associates some kind of mapping in between a given group, onto another group, and that group can be retrieved from a normal subgroup of the given group. Okay, and that is very much interesting in the theory of groups, and let's see how does it work. So first of all, let us explore some important facts out of normal subgroups. So yeah, so the first fact will be that for any group, G, you will have immediately two normal subgroups. So the singleton E and the whole group G are evidently normal subgroups of G. So these are trivial normal subgroups. You don't have to check whether it is normal or not. It is always normal in the given group. Okay. Fact 2 is that now if you consider an abelian group, then eventually every subgroup of this group will be normal, right? As because if G belongs to capital G, the given group, and N belongs to capital N, the given subgroup, you will see that Gn G inverse, so it is actually G inverse N, since the group is abelian. So it is En, that is N, and N belongs to N. And this is true for all G belongs to capital G. So this means that the set G and G inverse is a subset of N. Okay. So hence N be normal. Okay. Fine. Fact 3. Suppose you have you have a subgroup H of a group G having index means the number of left or right cosets of H in G having index 2. Then you can conclude that H is normal. Why? As because since the index is 2, and if you consider left coset decomposition and right coset decomposition of the group, then you will see that since the index is 2, so you must have the decomposition like that. So H union H or H union HA, where this A does not belong to H, right? Because the number of left cosets or right cosets is 2, only 2. And H itself is a left coset or right cosets of H in G, right? So you must consider another left coset or right cosets that can be taken as H and HA. Okay. Okay. So then we claim that H must be HA, right? Why? What is the reason behind that? Because every element of H, because suppose you consider H belongs to capital H, okay? Then this element being an element of G, so it must be in either in H or in HA, right? Because these are two distinct right cosets. So either it is in H or in HA. Now since A does not belongs to H, so this H must not be in the capital H, right? Right? So then H belongs to HA, as because A does not belong to H. So this H will not go to capital H, it will go to this right coset. So this means H is a subset of HA. And in a similar way, HA must be H. So hence, combining these two, you will have H equal to H. So this proves that H must be normal, because every left coset is a right coset and conversion, right? So hence H is normal. So thus H becomes a normal subgroup of G. Okay. Now we have already seen that in fact 2 that in an abelian group every subgroup is normal. Now one natural question will arise that does it happen in a non-abelian group? That means can you exhibit an example of a non-Abelian group in which every subgroup is normal? The answer is yes. So what is the model of the group? So let us have a look. So it is fact 4, the Quaternion group. Quaternion group. So how can it be constructed? So you can construct this group in this way. Suppose we consider a set G in which the in which we consider symbols like that, one, or objects, you can say objects. So 1 minus 1, I minus I, j minus j, k minus k. These are actually symbols now. This minus is actually a symbol. I am exhibiting this object like that. Okay, just use this symbol and putting a hyphen uh, before that. Okay, just like that. This is a symbol, first of all, where I, j, k are symbols satisfying the following relations. What are the relations? If you consider I square, I square means just put I consecutively. Okay, just I. So this will be minus 1. You are defining these relations, that if you put I and I together, then this will be minus 1. And the similar thing will happen to other symbols also. Okay. Also, if you put one I and j, then it will give you k. If you put first j and then I, then it will give you that symbol. And the similar relations can be defined for other cases in a cyclic order. That means if you put j k, so then it will be I, and if you put k j, then it will be minus I. If you put ki, then it is j, and if you change the cyclic order, it is ik, then it will be minus j. Okay. So with respect to these relations, we can define binary operation, that means the multiplication, using this following relations. Okay, so define the usual multiplication that has been considered in the for the case of numbers, the way we have defined multiplication of numbers will be copied here. Okay, so define usual multiplication on G, just like the way we are defining for numbers. Okay, with respect to the above relations. Okay, that means suppose for example, suppose you take I j k, right? So what would be I j k? Now you have defined j k as I, right? So it is I. Now what is I? I is minus 1. It is minus 1. So in this way, you can have all the multiplications, possible multiplication of these objects. Okay, using these following, using these above relations, right? And look at the relations we have defined. So these satisfy a cyclic order, right? So that means uh, so in physics we have considered this as right-handed system, right? That means suppose just I am giving you the indications, that is I, this is j, and this is k, right? So if you take ij, then it will give you k. If you take jk, then it will give you I, right? Now if you want to reverse the order, that is if you go just starting from I then go to k, then it will give you minus j, right? This one. So whenever you are reversing the cyclic order, it will give you 1 minus. Okay, fine. And so if we want to check, then we see that G forms a group with respect to the given multiplication. Okay, right? This group is known as Quaternion group. Okay, group of how many elements it has? Of order 8, right? Now you have seen up to now 3 groups of order 8. The first one was the cyclic group of order 8, that is Z8. The second one was the dihedral group order 4, which has also number of elements is 8. And the another one is this quaternion group of order 8. And this group So observe that. Just keeping in mind the construction that we have defined. So ij is k and ji is minus k. That means ij not equal to ji, right? So observe that G is non-abelian, right? So this is again an example of a non-abelian group of order 8. Although we have seen another non-abelian group of order 8, which is diagonal group of order 4, which has also 8 many elements, right? Fine. And this group has the special property that any subgroup of it will be normal. And we will see after a couple of minutes that every subgroup of uh, G is normal. Okay. Let us denote this group as Q8. That is the Quaternion group of order 8. Okay. Q8. And let H be a subgroup of Q8. We need to show that H must be normal, right? Now, using Lagrange's theorem, you will see that the order of H divides order of Q8. That means 8. So order of H is a divisor of 8. So the possibility of the order of the subgroup must be either it is 1, or it is 2, or it is 4, or it is 8, right? Right? Now if order of H is 1, then we are done, because H is a trivial subgroup containing the identity. Okay.
হ্যাঁ স্যার শুনতে পাচ্ছি।
So if order of H is 1, then we are done, because H will be a trivial group containing the identity, right? Now if order of H is 2, then then H can be written as, it is the identity. So here identity is 1, sorry. So it is 1 and some element A, right? Where A belongs to Q8 such that A is not equal to 1 and A square is 1. That is, the order of the element A is 2. Now if you look at the elements of Q8, you will see that the only element in Q8 which has order 2 is -1. So the only element of Q8 having order 2 is minus 1, which implies that H must be 1 minus 1, right? Right? Okay. Now, for any element, uh, x belongs to Q8. X is any element of Q8. Okay. Then what will happen? Then what is your left coset determined by x? Left coset of H determined by x. Then xh, what is xh? Xh is x minus x. Okay, equal to hx, as because why it is so? Because x dot minus 1, just you multiply x with minus 1, x with minus 1, then what will happen? So this will be minus x, right? And also you can write minus x as minus 1 dot x. And for the identity, it is obvious. And x1 is always equal to 1x equal to x, as because 1 is the identity, right? So for that reason, the xh equals with hx. That means the left cosets of h in G is are equal to the right cosets of h in G. So hence h is normal. So for normal in Q8. Okay. Okay. Now if order of h is 4, then by Lagrange's theorem, what is the index of Q8 colon h? It is the order of Q8 dividing by order of h. That means 8 by 4, that is 2. But we have already seen the fact 3 that if you have a subgroup of a group having index 2, then it must be normal. So this subgroup is of index 2. So this implies H must be normal in Q8. So if the order of the subgroup is 4, then we are done again. And for the last case, if order of H equals to 8, then H must be equal to order of equal to the whole group Q8, and hence H must be normal, right? In Q8. Okay. Okay. Fine. So thus we have proved that every subgroup of Q8 is normal. Okay. 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 Now, fact 5. What is fact 5? Now, I have defined already what you mean by the center of any group, right? So, let G be a group and ZG be its center. Okay, be the center. Okay, and we have already proved that ZG, so recall that ZG forms a subgroup. But now we will see that not only it is a subgroup, but also it forms a normal subgroup. Why? Because, so let G be any element of capital G and n belongs to ZG. Okay. Then now since n belongs to ZG, that means n commutes with every element of the group, and in particular n commutes with G. So then Ng equal to Gn. Okay, that means Gn G inverse is going to be n. So that means Gn G inverse belongs to Zg. Okay, and this is true for any G belongs to capital G. So this is true for any G belongs to capital G. So hence GZG G inverse is a subset of ZG, which implies that ZG is a normal subgroup of G. So so the center of any group is always normal. Okay. 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 Fine. Okay. Fact 6. Fact 6. What is that? That suppose H be a subgroup of a group G. Okay. Now define CH by, so it consists of those elements of a group G which satisfies the property that G commutes with every element of the subgroup H. Okay. So CH consists of those G which commutes with every element of the subgroup G, a subgroup H. Okay. And we have already proved, so recall that CH forms a subgroup of G containing H. Okay. Now observe that H is any subgroup of the group G. Maybe it is normal or maybe it is not normal in the group G, but whatever it is, H will always be a normal subgroup of this group. Okay. Observe that H is normal in CH. Why? Since for any G belongs to CH and H belongs to capital H, we have, then what will happen? Now since G is in CH, so it commutes with H, then GH equal to HG. That means GH inverse equal to H, which is in H. And this is true for all G belongs to CH, right? So that means GH, G inverse is a subset of H for all G belongs to CH. And this implies H is normal in CH. Okay? And this CH is called, this group is called the centralizer. The centralizer of H in G. Okay? And again, now if we define the set NH, what does it mean? NH is the set of all those elements of the group G for which the corresponding left and right cosets are equal. That is GH equal to H. Okay. So NH consists of those elements of the group for which the corresponding left and right cosets are equal. Then we can prove that NH forms a subgroup forms a subgroup of G containing H. H as a normal subgroup, right? Because as a normal subgroup. Why? Right? Because if you take any G from NH, then it will satisfy this property that the corresponding left and right cosets are equal. So H is normal in NH, right? Not only that, NH is the largest subgroup of G containing H as a normal subgroup. Why? As for if K be a subgroup of G containing H as a normal subgroup, then we see that for all x belongs to K, we must have xh equal to hx, right? Because h is normal in K. So that means for all x belongs to K, xh must be equal to hx. But in turn, it implies that now since xh equal to hx, so that x must be in NH. That is, K is a subset of NH. And this proves that NH is the largest subgroup of G containing H as a normal subgroup. Okay? This NH is called the normalizer of H in G. Okay? So this is called the normalizer of H in G. Okay? Okay. And the question is that, do you find any comparison between these two groups, that is centralizer and normalizer of a subgroup in a group G? Can we establish any comparison between these two concepts, that is normalizer and centralizer of a subgroup of a group? So suppose you have, so if you have a subgroup H of a group G, then you will have, so H will give you normalizer and centralization. So can we establish any kind of relationship in between these two subgroups of G? Both are subgroups of G, right? So just think on your own, okay? I would like to left this as an exercise. Okay? Okay. Now I would like to give you uh, one or two problems. That is, uh, note that if you can prove this, note that uh, for any group G, ZG will be the intersection of all normalizer of the element A. A belongs to G. So ZG is the intersection of all normalizer of A belongs to G. If you can prove that, then it is good. So this can be left as an exercise. Okay. Secondly, the problem is that show that the center of S3 is trivial. Can you generalize this to any n which is greater or equal to 3? Okay. Is it true for any n greater or equal to 3 that the center of Sn is the identity? Okay, so it is again a good problem. Another one is, can you show that the intersection of a collection of normal subgroups of a group is again a normal subgroup of G. Okay. Okay, fine. Now I would like to move our discussion towards the construction of new groups out of the old ones in view of normal subgroups of the given group. Okay. Okay. So for any now, yeah. So I would like to discuss on quotient groups. Okay. Now it is obvious that if you can remember that any equivalence relation defined on a set will partition the given set X, right? in terms of distinct equivalence classes. And we have defined the distinct set of all distinct equivalence classes with respect to the equivalence relation defined on the set X as quotient set. So for the case of groups, if you consider a group G and a subgroup H, then you can define two operations, two equivalence relations. One is for which will generate left cosets, and another one will generate right cosets. So if you consider the two sets, one is the set of all left cosets of H in G and another one is the set of all right cosets of H in G, then you can define the product of two left cosets, product of two right cosets. Okay, right? Now the question is that does it give you a well-defined relation, well-defined function? Does this product is well-defined? If not, then under which condition this product will give you well-defined operation? And the condition is that you need to consider normal subgroups rather than any subgroup. Okay, you need to consider normal subgroups. Okay, so let's have a look on that. So recall that I have already shown you that for any, recall that if you consider normal subgroups of a group G, then product of any two left cosets or right cosets, whatever you consider, of the given subgroup in G is again a left coset or a right coset, right, of the subgroup in G, right? So this tells you that, so if you consider the product operation, then this will give you a binary operation on the set of all distinct left cosets or the set of all distinct right cosets of the given subgroup H in G, whenever H is normal. And with respect to this binary operation, the set of all distinct left cosets or the set of all distinct right cosets, whatever it may be, because if you consider normal subgroups, then these two sets will coincide because every left coset is a right coset, right? So therefore, so that said, the set of all distinct cosets, whether you are considering left or right, whatever you are considering, that doesn't matter for us, but the set of all distinct cosets under this binary operation will form a group, and this group will be called quotient group of G out of the normal subgroup H. Okay, so let's have a look on the construction. So okay, Okay. So yeah. So let n be a normal subgroup of a group G, and let us denote G slash n y, which consists of all distinct left cosets, or if you can consider also right cosets. A belongs to sorry, G, G belongs to capital G. So G y n consists of all those distinct left cosets of n in G. Okay, this is a set of all distinct left cosets of n in G. Right. Now we define the product operation on G y n by Gn dot G dash n equal to G G dash n. Okay, right? G G dash n for all G comma G dash belongs to capital G, right? Okay. Then okay. So this shows that dot is closed under sorry, G by n is closed under the product operation, right? Because if you take any two left coset in G by n, then the resulting set is again a left coset of n in G, right? So G G dash n. Okay. Also for G G dash G double dash belongs to G, you will have Gn dot G dash n dot G double dash n. It is equal to G G dash n so it is equal to G G dash G double dash, right? Now since G itself being a group, so it satisfies associativity. So that means inside this bracket you will going to have G G dash G double dash. So shifting the bracket from G G dash to G dash G double dash. So it will give you Gn and G dash G double dash n. So that means Gn, and in the bracket this G dash n dot G double dash. So in this way, you will see that associativity holds with respect to the product operation. Okay, so this implies associativity holds for dot. Okay, now we need to have an element which will satisfy the property of being an identity. Right? So also, if we consider the coset n, now what is n? N can be written as en. Then we see that then for any G, Gn dot n, that is Gn dot En, that means Gen, right? So it gives you Gn. Again, n dot Gn, so again it will be Gn. So that means n, so this implies n is the identity element with respect to dot in Gyn. Okay? So it satisfies, or dot satisfies the existence of identity property axiom in the set Gyn. And the last of all is existence of inverse. And now for any G belongs to capital G. Now since G belongs to capital G and G being a group, so G inverse belongs to, so G inverse exists, and then you consider the corresponding left cosine, G inverse n, and then take the product of Gn with respect with the G inverse n. Then it will give you G inverse n. So that means what is G inverse? That is identity. So it is n. So that means the product of Gn with G inverse n is going to be the identity of the uh, operation in the set Gyn. Okay, and then again G inverse n Gn. So it is G inverse Gn. So again it is En. So again it is n. So this implies the inverse exists, and the inverse of Gn is G inverse n. And this proves that Gyn forms a group with respect to the product operation. For left cosets, or you can take it right cosets. Okay, and this group is called, this group will be defined as the quotient group of G by the normal subgroup n. Okay, fine. So this one I would like to stop here.